Let us now consider the variation of L and ml for a given value of the principal quantum number. Let us say that the principal quantum number is now 2. When n is equal to 2, the orbital angular momentum quantum number can take two values, 0 and 1. In general, L can take values from 0 to n minus 1. So since n is equal to 2, it can take two values, 0 and 1. When L equal to 0, the corresponding wave function is given the name S orbital, and when L equal to 1, the corresponding wave function is given the name P orbital. Please notice that L decides the magnitude of the angular momentum. So very clearly, when you put L equal to 0, the magnitude of the angular momentum is given by the formula L into L plus 1 into h by 2 pi. So when you put L equal to 0 here, it becomes 0 into h by 2 pi, which means that the angular momentum is 0. Similarly, when you put L equal to 1, which is what I have done here, it is 1 into 1 plus 1 h by 2 pi, which is, root 2 h by 2 pi, which is root 2 h by 2 pi. Root 2 h by 2 pi is the magnitude of the angular momentum when L is equal to 1. When L is equal to 0, the angular momentum has only one component along the z-axis, which is given by ml equal to 0. But when L is equal to 1, the z components of the angular momentum are given by the quantum number ml, which is minus 1, 0 and plus 1. Please notice that when L is equal to 0, ml equal to 0, and when L equal to 1, ml can take the value minus 1, 0, plus 1. That is from minus L to plus L to a total of 2L plus 1 values. Then you will be curious to know what is the implication of ml. What is ml telling you? See, the magnetic quantum number ml is telling us the z component of the angular momentum, whereas L is telling us simply about the angular momentum and its magnitude. So L decides the angular momentum, but ml decides the z component, that is the angular momentum along a particular axis which we have chosen as the z-axis. So therefore, suppose you consider L equal to 1. When L is equal to 1, the angular momentum is given by root 2 into h by 2 pi. This is quite well known. When this angular momentum is considered along an arbitrary axis called as the z-axis, then we consider the z components. There are three z components possible. One given by ml equal to 0, another given by ml equal to minus 1, another given by ml equal to plus 1. You will see that all the three are vectors, but their magnitudes are same, only directions of the z components are different. When ml equal to 0, the z component of the angular momentum is also 0, which means that there is no z component. And when ml is equal to plus 1, the z component is plus 1 into h by 2 pi, and when ml is equal to minus 1, the z component is minus 1 into h by 2 pi. Clearly, the magnetic quantum number is giving us three possible orientations along the z-axis. When L equal to 1, there are three possible orientations. One along the z-axis itself, which is given by ml equal to 0. Since the rotation is now along the z-axis, okay, it is along the z-axis, therefore the z component is 0. Another like this and another like this. Remember that we have considered all these when dealing with the rotation of a particle in 3 dimensions. There we clearly saw that the orientation of a circular path or a spherical path about a z-axis leads to different components along the z-axis. So therefore, the values of ml are in turn controlled by L. Let me now summarize once again the significance of the three quantum numbers that we have derived. The first quantum number, namely the principal quantum number, tells us the energy of the orbital. Secondly, the azimuthal quantum number or the orbital quantum number tells us about the angular momentum of the electron orbit or orbital. And the magnetic quantum number tells us about the z component of the orbital angular momentum. In other words, it tells us the orientation of the orbitals. Now you would have noticed that in the last 7 to 10 minutes, I have been using the word orbitals without actually defining them. I have done this because directly or indirectly we all know the meaning of the word orbital, but now that we are in a position to actually define it based on solving the Schrodinger equation, we will pause for a minute and try to ask ourselves, what is an orbital? After all, what we have done, we have taken a one electron system, that means a system having only one electron, written the Schrodinger equation for this, and then solved it. Upon solving, we will get the wave functions. There will be obviously different wave functions, and for each wave function there will be a corresponding energy value. These different wave functions of the one electron system is given the name orbital. Therefore, orbitals are the solutions of the Schrodinger equation written for a one electron system. So when you solve the Schrodinger equation for a one electron system, you may end up getting psi 1, psi 2, psi 3, psi 4, psi 5, and each psi is called as an orbital. But unlike in the motion of a particle in one dimension, where psi depended only on one quantum number, now the psi depends on three quantum numbers. And therefore, if I have written it here, you can notice that the wave function which depends on n equal to 2, L equal to 0 and ml equal to 0 is called 2s. So it is also called, in fact you can give the subscript as psi 2s. Similarly, if you want to write the 1s orbital, for 1s orbital it is nothing but n equal to 1, L equal to 0 and ml also equal to 0. So psi 100 is given the name 1s orbital, psi 200 is given the name 2s orbital. Similarly, psi 210, n equal to 2, L equal to 1, ml equal to 0 is given the name 2pz orbital. 21 plus 1 is called 2px and 21 minus 1 is called 2py. We will shortly see why three orbitals are called pz, px and py. We will of course also deal with the shapes of s orbital and the shapes of p and d orbitals. But what is very important for us to realize is that the wave functions that we obtain on solving the one electron system give us the orbitals, and these orbitals are given the various labels as s, p, d and f based on the values of the quantum numbers. When L equal to 0, we call it as an s orbital, L equal to 1 we call it as a p orbital, L equal to 2 we call it as a d orbital, L equal to 3 we call it as an f orbital. And based on the n value, based on the distance which is given by r, and from r we get n, so therefore based on distance the s orbital is further labeled as 1s, which is closer to the nucleus, 2s a little farther away, 3s much farther away, so on and so forth. Similarly, you have 2p, 3p, 4p, 3d, 4d, 5d, 4f, 5f, 6f, so on and so forth. So therefore, the entire picture is obtained by combining two factors. One factor tells us the variation of psi with distance. Another factor tells us the variation of psi with angle. So in order to arrive at an integrated picture, we need to combine both these variables, namely the distance factor and the angle factor. And both these will be discussed under the heading of radial distribution function and angular distribution function in the slide that follows.